So you basically launch these machines and they have the right geometry, mass distribution. And if you launch them just right, they'll actually walk downhill without falling down. Okay, so there is no motor needed. You just supply it energy by tilting the platform in the right angle. Okay, and that's what we're going to do using external power, except for, of course, gravity. So passive dynamic walker is a machine that walks down a ramp without any external power or energy. Okay, and then of course, if you look at YouTube, you search for passive dynamic runner, then there are videos of some of these machines actually running downhill without using external power energy. And so what we have in mind is basically a caricature of this robot in terms of a double pendulum, but the double pendulum is in this configuration. Okay, so let's make one of the legs dark and let me make the other one red perhaps. So you can think of it starting in this position when this leg is swinging forward. It's still moving forward. At some point of time, the red one, or the leg which is moving forward, hits the ground and collides with the ground. So the collision, and then we will have this thing which is basically now the red leg becomes the leg on the ground, the black leg swings. Okay, so sort of you can see that this is the same thing. Looks very same, right? It basically switches roles and it keeps going. So this is basically what is known as periodic walking, which is you started the configuration, it goes through this intermediate configurations, end up in the same configuration, and this basically keeps repeating till this system keeps doing that till the ramp finishes off. So before we can actually go and analyze passive dynamic walkers, there are some tools from dynamical systems which we should know about. And there are just 3 of them, and I'll talk them and then we'll stop. Okay. So one thing is what is known as a Poincare. The Poincare should be this way. Section and map. So there's a Poincare section and a Poincare map, and it's basically something like this. So you take this system, take any point on the system which I just drew, okay, and we'll trace the motion of that point. So it starts somewhere, let's say at some point xi, okay, where this is clearly our xi. Okay, this is xi is the state. So in this case, there were 2 links. There is two state variables. So it's a high dimensional state describing the joints or something about the system. And then we trace its path after one step. So this is xi plus 1. So this particular place where we are looking at the system, okay, so you can see that this configuration is the same at this configuration. So this is basically a Poincare map, sorry, Poincare section. Okay, it's an instant in the locomotion cycle at which we are going to take a sort of a snapshot of the system. Okay, and usually there are certain instances which are favorable, like for example an instant where both legs touch the ground. That's a good instant which people use. Another good instant is when the leg is vertical, when the angle made by one of the leg with the gravity is zero. But you don't have to restrict to them. So that's basically a Poincare section. Okay, we are trying to take snapshots of the robot at the Poincare section. So what we can think of is, if I have this xi, okay, which is this xi, then it goes through this, undergoes this motion, and those motion is described by Newton's laws, or using Euler-Lagrange method. Then we can find a function f such that we can use this function to describe the position of all joints after one step. So this f is known as a Poincare map. Okay, most times it's not possible to find an analytical function f. You have to resort to numerical methods. Okay, okay, so that's the Poincare map. So next thing, once we have the Poincare section, Poincare map, then we can think of what is known as a fixed point. Okay, so now what if I told you that there is a certain, let's show the thing, draw off the figure again. We started, and what if we start it such a way x0 such that after one step we're back to the same state. So xi plus 1 is x0. So a Poincare section, a Poincare section is right there. And then we ended up the same place. So what we can do now is write x0 is f x0. So what we have in general is that x0 is periodic, right? And so this thing is known as a limit cycle. Here, limit cycle is basically a sort of a periodic motion of whatever system we're looking at. And that the way we look at the periodic motion is we look at what happens to the system after one step on the Poincare section. Okay. So this is the limit cycle, the red. And then this point, x0, is called a fixed point. The next important thing we need to know is the stability of the fixed point. In fact, we'll only focus on linearized stability. Okay, so when is a fixed point considered stable? Well, if you take x0 and you perturb the system, say x0 plus delta x, okay, where delta x is small, then you ask the question, where is xi? So this is xi. So instead of starting at x0, you started at x0 plus delta x. And then you ask the question, what happens to xi plus 1? Is it close enough to x0 or not? If it's going away from x0, so going away from x0, then the system is unstable, right? If it's going towards, then the system is stable. Okay, so instead of really checking this for all possible perturbations of x0, that is basically delta x, what you do is you basically find what is known as a Jacobian. Okay, now the Jacobian here is slightly different from the Jacobian we talked about. It's basically is the way we think of Jacobian here is the first derivative of f of the Poincare map with respect to x, and we validated at x equals x0. So this is the derivative, the first derivative of f, Poincare map, with respect to uh, state. The state is x. Okay, and then we say that if df by dx or j is greater than 1, then the system is unstable. If the system is less than 1, it's stable. And if it's equal to 1, it's neutrally stable. So this is a check on the stability of the system by by avoiding by actually avoiding to do this delta x perturbations and seeing the response. And then we evaluate that state at x equals x0, which is basically the fixed point. If j, or I should, well, j is basically going to be a matrix. So what we need to do is we need to find the eigenvalues of j. And that's actually very simple. In MATLAB, there is just a command called eig, which can help you do that. Okay, so what we do is we find the maximum eigenvalue of j. And if that's greater than 1, then we say the system is unstable. If the maximum eigenvalue is less than 1, it's stable. And if the maximum eigenvalue is equal to 1, then we call it neutrally stable. When I say the maximum value, it really means the absolute value. Okay, so maximum, or we can say max eigenvalue and the magnitude. Okay, so what I'll do next is illustrate uh, this particular idea with a simple example. Okay, instead of looking at a limit cycle and walking, I'll look at a simple function f and see how we can understand this concept intuitively. Okay, so example. Okay, so consider this state. X I plus 1 x I plus 1 equals f of xi, where f of xi is 2xi, sorry, xi square. Okay, so f is here xi. Okay, and the question is find the fixed points and their stability. Okay, so that's the question. However, let's do this intuitively. Okay, okay, so if this, let's just do the experiment where we throw at xi different inputs and then see what happens to xi plus 1 for certain ranges of xi. So let's choose uh, xi between 0 and 1, any number between 0 and 1, and then see what happens to this function. Okay, and then similarly what we'll do is we'll choose xi greater than 1 and see what happens to xi square. Okay, so I'm just going to use a square and then keep iterating over that. So let's choose a value for xi less than 1 but greater than 0. So let's choose let's say 0.1. Okay, and then I need to square it. Okay, so it's 0.01. Now I need to square that again to do the next iteration, and I get 0.001. And then if I keep doing this, you can see that the number gets smaller and smaller, which clearly means that the solution is closing into 0. Okay, we can try this for some other value. Let's take, for example, 0.9, okay, and take square of it as 0.81. Take square of that again, the next iteration, 0.65, 0.43, 0.18, 0.03, 0.001, and then you see that it just keeps dying out, eventually becomes 0. So you can see that for x between 0 and 1, we end up with something which is close to 0 after running this calculator multiple times. Now if we choose xi greater than 1, let's start with 1.1 and then do the square, and you can see that it's growing. X square of that 1.46, 2.14, 4.59, and then it just blows up, just goes to infinity. So you can clearly see that there's a behavior of this function, which is if it's between 0 and 1, it converges to 0. If it's greater than 1, it diverges actually becomes infinity. This xi plus 1 tends to 0. In this case, xi plus 1 tends to infinity. Okay, so we can say that this is stable, this is unstable. Okay, so here is that's the intuition, here's the math. So first of all, find fixed points. So what are fixed point? Well, it's basically the solution to this particular equation, right? X0 is f of x0. So let's just do that. So x0 minus f of x0 is equal to 0. So we have x0 minus f of x0 is 2x, sorry, x0 square equals 0. We can pull out the x0, and then we can see there are two solutions. One of them is x0 equals 0 and x0 equals 1. Or in other words, there are two fixed points or two fixed points. So that answers the first part of the question. Now let's go to the stability. Okay, so we have uh, f of x equals x square. So we need to find the Jacobian, which is df dx, that's 2x. Now, if we find the Jacobian at x equals 0, we have 2 times 0 is 0, which is less than 1. This means that x 0 equals 0 is the stable fixed point because the eigenvalue, or in this case, the eigenvalue is the absolute value, is less than 1. We can also find the eigenvalue at x equals 1. We have 2 times 1, which is 2, greater than 1. x0 equals 1 is unstable. Okay, so we got the same result using the math. Right, this is the result we had, and this is the result we got using the math, the same thing. Okay, so this is sort of the giving the intuition of using fixed point and using the Jacobian to do the calculation.